Ever wish you could just like hop in a time machine and rewrite history? Or maybe just relive that perfect day at the beach?
Who hasn't?
Right. Well, today we're diving into the wild world of time travel, but get this, we're leaving the DeLorean and flux capacitors behind.
That's right. We're tackling the mind-bending idea of time travel without time itself.
Okay, now you've really piqued my curiosity.
It's a concept that really pushes the very boundaries of how we understand reality.
To navigate this intellectual wormhole, we're warping straight into a research paper called Emergent Time and Time Travel in Quantum Physics.
And it's a fascinating one.
And let me tell you, this isn't your average bedtime reading. So, what's this paper all about?
Well, it really challenges a fundamental head-scratcher in physics.
Hmm.
This conflict between how we humans experience time and what our current physics equations tell us about it.
Right, like when you're stuck in traffic, time seems to crawl, but when you're having fun, it flies by.
Exactly.
Sadly, physics doesn't seem to care about our feelings.
Exactly. Our everyday experience suggests time is this constant flowing river. But at the quantum level, the very foundation of the universe, that river starts to look more like a choppy ocean, or maybe even a puddle.
Okay.
This is what physicists call the problem of time.
So, are you saying our whole concept of time might be wrong?
Not necessarily wrong, but perhaps incomplete. You see, many arguments against time travel rely on this common sense view of time as a straight line.
Right.
But what if that line is just an illusion? A side effect of something much stranger happening beneath the surface.
Okay, now my brain is officially doing backflips. Before we tumble too far down the rabbit hole, can we rewind a bit? Where does this radical new view of time even come from?
It emerges from the mind-boggling world of quantum physics. You know, all those concepts that make you question everything you thought you knew about reality.
Oh, you mean like quantum superposition, where something can be in two places at once?
Precisely. Imagine a coin spinning in the air. It's not just heads or tails until it lands. In the quantum world, it's both heads and tails simultaneously.
Okay.
And it gets even weirder with entanglement.
Entanglement. Refresh my memory on that one.
Imagine two of those spinning coins, but here's the kicker. No matter how far apart you separate them, even across galaxies, if you know the state of one coin, say it landed on heads, you instantly know the other landed on tails. They're linked in this spooky, distance-defying dance.
Okay, that's seriously trippy. I can see why quantum physics is a goldmine for sci-fi writers.
It is.
But how does all of this tie back to our time travel conundrum?
Well, these mind-bending quantum phenomena hint at a universe far stranger than our everyday intuition would suggest. And it's within this strange, counterintuitive world that a new way of thinking about time emerges, a framework called the Page-Wootters Formalism, or PW for short.
Page-Wootters sounds like a fancy law firm. What's their take on time?
Think about a clock, not as a device measuring some independent time flowing around it, but as its own little universe. The hands move, the gears turn, a process unfolds within that closed system. We interpret that process as the passage of time.
So instead of time being this external thing that everything exists in, the PW formalism says it might be more like the internal mechanism of a clock.
That's a great way to put it. PW suggests that maybe the universe is like that clock. Time isn't fundamental, but rather it emerges from the interactions and evolutions of the quantum systems within it.
Whoa. So are we saying goodbye to the space-time continuum as we know it? If time is emergent, does that mean we can manipulate it, control it?
That's where things get really interesting. And to delve into that, we need to explore the toy universe that these researchers created.
A toy universe, like a quantum Lego set.
Not quite, but I like your thinking. Imagine two interconnected harmonic oscillators. Picture two pendulums swinging in perfect sync, forever intertwined in their movements. They have a fixed total energy between them, like a mini-universe governed by its own set of rules. It's fascinating.
Okay, I'm visualizing these synchronized pendulums. What makes them so special?
This setup, as simplified as it seems, lets us explore the profound implications of emergent time. And it's within this model that the researchers found something truly remarkable, something that challenges our very definition of what time travel could be.
Okay, now you have to tell me more. What did they find? Did these pendulums suddenly transform into a time machine?
Not exactly a time machine, but they discovered that even within this model where time is emergent, certain conditions make it seem like one of the oscillators is traveling through time relative to the other.
Wait, hold on. How can something time travel if time itself isn't a fixed backdrop? It's like saying you can walk east without there being an east to walk towards.
Right.
Yeah.
That's the mind-bending part. It's not about traveling through time as we traditionally imagine it, but rather about how these quantum systems can evolve in relation to one another. Imagine two dancers moving in perfect synchronization.
Okay.
They're a unified system, their movements intertwined. Now, imagine that one dancer suddenly reverses their every step, like rewinding a film, while the other continues dancing forward.
Interesting.
Yeah.
So even though they're both part of the same dance, their experiences within that dance become vastly different.
Precisely.
Yeah.
And that's a lot like what's happening with these oscillators. Even though there's no external time that either of them is moving through, one can evolve in a way that appears reversed relative to the other. It's like their internal dances are defining their experiences of time rather than some universal metronome.
Wow. That's both fascinating and confusing in the best way possible. But does this mean that building a time machine is actually within the realm of possibility?
Hold your horses.
Yeah.
Before we start planning our trips to the past, we need to remember this is still a simplified model.
Right.
It's a peek through the keyhole, not the whole picture.
So no DeLorean just yet. But this time travel within the toy universe, what are the implications of that? Does it upend everything we thought we knew about cause and effect?
That's exactly the kind of question this research makes us ask. And to understand the potential answers, we need to explore something called Novikov's self-consistency principle. But we can delve into that more after a quick break.
Okay, Mafikakov's self-consistency principle. It sounds kind of like something straight out of a physics textbook.
It's a mind-bending idea,
Mhm.
but really cool once you wrap your head around it. Imagine you could travel back in time.
Okay.
Novikov's self-consistency principle basically says that whatever you did in the past, you already did. Your actions in the past are already woven into the fabric of how you got to the present.
So it's like saying no matter how hard you try, you can't change the past because it's the past that led to your present self who's now trying to change it.
Exactly. It's a bit of a temporal paradox, but
Yeah.
the principle suggests that the universe has a way of self-correcting. Like if you tried to go back and prevent a historical event from happening,
Right.
something would always prevent you from succeeding because that event not happening would contradict the very timeline you come from.
Okay, I'm starting to get it. It's like the universe has a built-in safeguard against paradoxes, ensuring that even if time travel were possible, it wouldn't unravel the fabric of reality as we know it. But how does this connect to the bland version you mentioned earlier, the one related to our pendulum friends?
That's where the findings of this research get even more intriguing. Remember how in their model, one oscillator could evolve in reverse relative to the other, mimicking a form of time travel? Well, their calculations suggest that this type of time travel would also adhere to a form of self-consistency, preventing any reality-breaking paradoxes.
So even in this toy universe where time is emergent, the rules seem to prevent us from going back and say, making sure we ace that history test we totally bombed.
It seems that way. Now, it's crucial to remember that we're working with a very simplified model.
Right.
Extrapolating from this to the complexities of our actual universe is a huge leap.
Right. No need to panic about predestined futures just yet. But it does make you wonder if this principle holds true in a broader sense. What does it say about our understanding of free will?
That's the million-dollar question, isn't it? If we can't change the past, even with theoretical time travel, does that mean our choices in the present are predetermined? Is free will an illusion? These are questions philosophers have grappled with for centuries, and this research just adds another layer of complexity to the debate.
It's enough to make your head spin. Though I have to admit, it's exhilarating to dive into such profound questions. It really highlights how much we still don't know about the universe and our place in it. But back to the science for a moment. Where do we go from here? What are the next steps in unraveling this mind-boggling connection between quantum physics and time?
This research opens up a treasure trove of possibilities for further exploration. For one, we could try to scale up this model, moving beyond our simple oscillators to more complex systems that better resemble the universe as we observe it.
So from a pendulum universe to something a bit more life-sized.
Exactly. Imagine applying these principles to systems involving not just two, but countless particles interacting across vast stretches of space and time. The possibilities are both daunting and exhilarating.
Daunting, for sure, but also exciting to think that we're just scratching the surface of understanding something as fundamental as time. What else is there to uncover?
Well, we could also delve deeper into the implications of this bland version of Novikov's self-consistency principle. If paradoxes are truly impossible, does that mean the universe is fundamentally deterministic? Do we have free will in any meaningful sense, or are we all just along for the ride?
Big existential questions. And I suspect we're not going to have definitive answers anytime soon. But even wrestling with these questions, pushing the boundaries of our understanding, isn't that what science is all about?
Absolutely. It's the journey of discovery, the constant questioning and exploration that truly pushes us forward. And who knows, what seems like mind-bending theoretical physics today could be tomorrow's common knowledge. Just look at how much our understanding of the universe has changed in the last century alone.
That's a really great point. What once seemed like science fiction like landing on the moon or the very device we're using to record this podcast is now a reality. It makes you wonder what incredible breakthroughs await us just around the corner.
Indeed. And that sense of wonder, that insatiable curiosity to unravel the mysteries of the universe, is what drives us forward.
It's like that old saying, the more you know, the more you realize you don't know. Except in this case, what we don't know about the universe could rewrite everything.
It's true. Every answer seems to unlock a dozen new questions, but that's what makes this journey so captivating.
Yeah.
Who could have imagined a century ago that our exploration of time would lead us to quantum oscillators and the very nature of reality itself?
It's mind-blowing to think that we're even contemplating these concepts. Before we started this deep dive, the idea of time travel without time seemed like pure science fiction, you know? But now it feels like we've caught a glimpse of something truly profound, even if it's still shrouded in mystery.
It's like we've stepped through a doorway into a realm where the seemingly impossible starts to feel, well, tantalizingly within reach.
Yeah.
It's a powerful reminder that the universe is far stranger and far more wondrous than we could ever imagine.
Absolutely. And a reminder that our understanding of the universe is constantly evolving. What seems impossible today could be tomorrow's groundbreaking discovery.
And perhaps someday, we'll look back on these early explorations of emergent time with the same fondness we now reserve for, the pioneers who first dared to imagine a world with electricity or computers.
It makes you wonder what future generations will be pondering about the universe that we haven't even begun to imagine. But for now, I think we've given our listeners plenty to chew on.
Indeed. If this deep dive has sparked your curiosity even a little, I encourage you to explore further. Read the research, ask questions, and never stop questioning what you think you know about the universe.
Well said. A huge thank you to you for being our guide through this incredible landscape of quantum physics, emergent time, and the mind-bending possibilities of a universe where time travel in some form might actually be possible.
It's been my absolute pleasure. Until next time, keep exploring.
And to our listeners, remember, reality is often stranger than fiction, especially when you're exploring the deep dive. We'll see you next time for another adventure into the unknown.